Does the concept of Earth's sphere apply to the universe as well? If we set out on a long journey from any point on the surface of the Earth and traveled in a straight line to the farthest distance possible, we will eventually reach the same point from which we started our journey. After a journey in which we travel about 40,000 kilometers, 25,000 miles, across mountains, oceans, deserts and rivers, we will have completed a complete journey around the surface of the planet. The final stop we will reach will undoubtedly be the point where we started traveling. Is the same way applies to space? If we went on a spacecraft in one direction, and to what distance do we choose, will we eventually return to the same starting point? It is an interesting question. Even when all indications point to it no possibility, but there are two ways in which the answer may seem yes. When we leave our house and look at the Earth around us, it generally appears flat. Because as far as we look in every direction, and from anywhere a person is on the ground, we cannot directly discover the curvature of the Earth. This does not mean that the Earth is not spherical, it does mean that if we want to discover and measure exactly how much Earth is curved, we will need to look at it on a wider scale than our eyes can look at from one observation point. Fortunately, there are several ways in which we can effectively collect the information necessary to show the spherical Earth. We can measure a specific object with different latitude and longitude. Or, if we want, we can immediately travel to a height sufficient so that we can see the curvature of our planet directly. And when we come to the universe, the situation is more complicated. By seeing us in the Milky Way, even with all the sensors sent across and outside the solar system, we cannot directly measure whether the universe is flat or curved. What we can only do is measure the light that comes from far sources away from us, millions or even billions of light years away. If the universe is curved, then those light paths will be curved in a certain way, but if the universe is flat, then these light paths will present us with different shapes. Through galaxies, galaxy clusters, and even the light remaining from the Big Bang itself, the cosmic microwave background, we can indirectly determine that the universe is flat. And if the universe is spherical, like Earth, then the radius of curvature is at least hundreds of times greater than the size of the observed universe. What appears on the surface indicates that the universe is flat, not curved. There is no indication that the universe is at least curved, within the range by which we can measure the universe, about 46 billion light-years in all directions from our observation point. But considering that the universe bends positively so that parallel lines meet, the way that parallel lines, such as longitude, are drawn on the surface of the Earth and that will meet at the end, is not the only way that our universe can bend. Alternatively, you can imagine that our universe took the form of a round torus or a long cylinder whose ends were tied to form a ring-like shape. Along the surface of the protrusion, the parallel lines will never meet and the measured deviation in the far light will be fully consistent with the flat universe. The only way we can distinguish between a protrusion-like universe and a three-dimensional universe is to find evidence for that unusual mathematical form known as topology. What would that look like? That means, if we went to deep galaxy surveys, large-scale assembly maps, or even the residual radiation from the Big Bang, we would be able to determine which region of space appears in multiple places. If the universe looked like a round bump and was less than 92 billion light-years from end to end, we would be able to determine which locations have the same characteristics in both places. Unfortunately, the universe does not show us that way. All sky maps are built to great depths, including a very detailed view of the cosmic microwave background maps. The properties we see are very rich with information about the nature of the universe, but they always represent distinct regions of space. If the universe really does somehow bend to itself, it can only do so on a scale larger than we imagine. Even if that were the case, we would never be able to cross the entire universe in that fashion. The reason is simple: the universe is expanding and the speed of its expansion means that even at the speed of light, there are limits to how far we will go. Although we can always travel for the longest amount of time and reach close to the speed of light, things that are currently beyond 18 billion light-years, about 94% of things in the observed universe, will forever remain beyond our reach. Still, it is always possible for the universe to be really curved upon itself like this, but only on a scale larger than we can imagine. It is possible that if we were able to travel endlessly, we would be able to perform this task. Perhaps, if we had traveled in a straight line to a sufficient distance, we would really go back to the starting point, just as if a shell had been fired exactly at the same speed on the ground and ignored air resistance, it might end with a blow to the head from behind after 90 minutes. The reason for this is gravity. Gravity pulls the curvature of the fabric of space, which means that when something moves in a straight line, it actually follows the curvature of the space through which it travels. If you are traveling on a correct path in the vicinity of something very broad, it is pushing you to return you to your original direction. Most things in the universe, such as planets, stars, or galaxies, whose gravitational effects can make objects moving at speeds close to the speed of light skew a little. It is enough to create multiple images of the distant object, due to the fact that multiple light paths exist from the source to the intended place, but not enough to make the light return back. One class of things that can do that is black holes. When light passes too close to the outer surface boundaries of black holes, it can deflect a very large amount, at a full 180 degrees. This was a very important element that led to the calculation of the shape of the first image of the Black Hole Boundary Telescope, because the behavior of light near black holes is very outside of our daily experience. That is the only realistic way we know, without assuming something contemplative about the unnoticed shape of the universe and giving up the constraints of the speed of light, is that we can travel straight and go back to our first point. The truth is that the presence of matter and energy bends space, and in some places, space bends so badly that it can dramatically change the course of an object. With the right choice, we may virtually get anywhere we choose by launching a spaceship with a good track and with appropriate knowledge of black holes across the galaxy and the universe. On a cosmic scale, there is no such sign that the universe is infinite and even. There is no evidence that properties in one region of space also appear in any other separate region, nor is there evidence of a repetition of the model in the large-scale construction of the universe or the remaining glow of the Big Bang. The only way we know to return a moving object is through gravitation slingshot, not cosmic curvature. However, there remains the possibility that the universe may in fact be limited in scope, but it is greater than what our observations can currently provide us. When the universe unfolds over the next billions of years, more and more of it, about 135% more, will become visible to us. The only hope for the discovery of a finite, transitable universe lies only, and paradoxically, in our far and distant future.